I know it feels like a long time, but let's continue our conversation with the Fourier expansion with one of the more important examples that we're going to do for this class, and that is a 50% duty cycle square wave. All right. So this one we're going to do mathematically. And so what is the DC offset, right? Remembering it's the average of the waveform. In this case, it's a 50% unit square wave, all right? So plugging that into the equation, right, it's actually discontinuous, all right? And so let's just double check that we remember what a 50% square wave is. So if that's time, right, that would be the period. It would be on for half the period, and it would go up to a value from 0. And this would repeat. All right. So in this case, it's just we're setting that constant equal to 1. And so we're going to integrate this, right, 0 to pi over 2. We're still averaging over the whole cycle, right? But in this regime, it's really just 1 dt. And then, yeah, the other half would be t divided by 2 to t, integrating 0, but that would go to 0. And that's what this says right here, right? I'm integrating for half the period, it's 1. For the other half, it's 0. And it turns out to be a half, right? The average of that, if that's 1 and it's on half the time, is a half. Great. Now let's find the other constants of the, so remembering the A's are the cosine and the B's will be multiplied by the sine. And yeah, so I know there's a DC offset here, right? Well, I can kind of, what's gonna be my best thing that will look like it'll fit in there, right? Well, that's a sine wave with a DC offset. A cosine would look like this. So I'm thinking, yeah, cosines aren't going to be a big part of this structure. They might all be 0, and sines should be. So we set up our equation xt. Remember, it's discontinuous, so we're going to integrate the first part, and then the second part, we're just going to leave b because it's always 0. So if like, where's the other part of the period? It's just, we know that it's 0 past half the period, and we're ignoring it. All right. So if we want to integrate cosine, we get sine, and we plug in 0 and half the period, and sine of 0 is always 0, and so is this part, this sine. So if you plugged in what omega naught would be, which is really 1 over 2 pi t, you'd see that this goes to 0 as well. All right. Oops. So that makes it fairly easy that we're only going to have sine waves. All right, how many? Let's see. So we plug it into the B equation to find the spectrum of the B's. Same thing, we're only integrating up to half the period. And we get this equation where we have 0 T naught divided by 2. So we have minus cosine of 0, right? So that'll always be minus 1. But this could either be plus 1 or minus 1 as well. And so what when n is such that this is a plus 1, these will cancel. When n is such that this is turns into minus 1, then they add. And so when does that happen? When n is odd. So when n is 1, 3, 5, 7, 11, 13, this reduces to b naught 2 divided by n pi. All right. So at 0 hertz, whatever this was would be divided by half. And so it's 1, then it's half, right? And then now what we can do is you can either do n pi divided by T1, or you could do omega 1, omega 2, omega 3, depending on how you do the units. But once you know that fundamental frequency, right, you can just do F1, F2, F3, F4, right? And the B constants are, and just let me double check. Two divided by n pi. So when n equals 1, right, I have 2 divided by 1 divided by pi. And so I get a value let's just call it 0.64. F2 is 0 that we stated before. Then we have another odd. So 2 divided by pi divided by 3. About 0.21. Oh, drew that in the wrong place. F4 is 0. And I'm just going to squeeze F5. .127. So remember, I said every repeating waveform can be summed up into from a series, an infinite series. The offset was a divided by 2. And in this example, there's only, sorry, okay. So in this example, this is only made up of sine waves that we keep adding up to each other to try to make this figure. And if we were to convert this to C values, right, which is another way of looking at it, a C value combines the sine and the cosine into one cosine with a phase, all right? And this is the formulation, right? You take the magnitude of the sine and the cosine, that's just using the magnitude, and then the phase, you just do that. Now, let's see what this really looks like. What I did is I created an LT spice file, and the fundamental frequency is 1 Hertz. And so then I have odd harmonics. So I have 3 Hertz, 5 Hertz, 7, 9, 11, and 13. All right, so I set the fundamental, and then I just start multiplying it by increasing odd numbers. I just set A naught equal to 1/2, and then I just calculate the B constant, right? So you can see the progression here, right? 2 divided by pi, 2/3 pi, 2/5 pi, 2/7, 2/9, 2/11, 2/13 pi. All right, now what does that mean? Well, now I have sine waves. All right, so here's a sine wave. B1 is the amplitude and F1 is the frequency. And you can see I just programmed this along. All right. Oop. And you can download this file and run it yourself. All right. And so I just start plotting things out. What if I just had A naught? Well, then I have a DC. That doesn't do too much. Right. But what if I had the DC plus the first term? Well, then I would have a sine wave with, notice, a DC offset. But oh, I don't want to do that. Either. So remember, the original waveform that we wanted, right, that we're saying we can build up is this square wave, right? And we can see that there's an error there. So let's add another term, right? So I'm added the first harmonic and then the third. And see, it gets a little bit closer. Then I add up to the fifth. It's getting closer. And you can see as I keep going higher and higher that in fact I'm getting closer and closer to the original sine wave, square wave. Now, doing it in this fashion, you'll actually never get the original wave. There'll always be some kind of ripple, and that's due to the fact that even though I have a 64-bit machine, I have finite precision arithmetic, and so there will be errors that creep in. So that if you reconstitute a wave this way, you'll kind of always see these ripples. And when I was using Scopy, I think, yeah, you almost have to take 50 terms before, if you put it into a filter, it'll start acting like you think it will. All right, but that's a lesson for another day. Okay, so let's just draw this a little bit bigger. So again, and this goes on for infinity, but it seems to me for a lot of cases, 50 is good. And even in Scopy, I think I was able to make a mathematical function with 100, right? Or I have certain things that I do in Python where I automate this process where rather than doing it one voltage source at a time. But this is very interesting. You take a square wave, right? And that square wave is a square wave, but these frequencies are there, right? The offset is there, the fundamental frequency is there. And not only that, it's higher than the DC average. And then it goes off. So we can use this to kind of generate signals with filters, right? So let's just review our filter shapes, right? And we'll just kind of do a abstract, right? And since it's a filter and it's the Bode plot kind of assumption, right? Yeah, it's frequency. And that's low pass, right? That's high. Band. Notch or band reject, right? So this will let all the frequencies through at some point. It'll start to get rid of higher frequencies. Here, it'll block lower and allow high pass. Here, it'll block some lower frequencies and higher frequencies and allow a particular band of frequencies in, and the notch or band rejects a certain band of frequencies. Now, as you might recall, I talked about RMS, right? Being what's the equivalent energy or so of this signal here so that we can compare it to DC, right? But now we're talking about an average, right? Not an average of the signal squared. All right. But it's a similar thing. Now, what if I wanted to keep, what if I had this square wave and I wanted to turn it into a DC power supply? What, and I'm asking this to the group now, which one of these filters would we use?
What was the question again?
So I have a square wave, right?
Yes.
And I want to put it through a filter. And rather than a square wave or a sine wave, I want it to be DC, meaning I just want a flat thing, or as flat as possible.
Then would it be a bandpass then?
So I'm labeling these so we all hear see the same thing. So where would you put your bandpass? A, B, C, D, E, F, G? Where? I'm
B.
getting a few B. All right, I'm getting a few B's. So this frequency, right? What would this look like in the time domain? Well, it would be, oops, excuse me. It would be, and I'm going to draw it, right? Centered around it. Okay, I want to keep that. All right, so what is that signal? Well, the amplitude would be A times 2 divided by pi sine 2 pi f1 t. All right, so I'm going to put in a square wave, right? So with a DC offset. And what I'm going to get out is a sine wave with an amplitude of A times 2 pi. So the sine wave, does that look like a DC?
No.
Okay.
No.
Now I'm curious, there were a lot of people who committed to band. I'm curious as to what the reasoning was. You guys can put it in the chat. That's okay. You can email me later. If you want to email me later for, your reason for selecting band, it goes up and goes down. Okay. So I'm going to put a band around C. Okay. So now I'm getting this. Well, that's just a sine wave at 2 pi 3 T F. So that's still a sine wave, right? It's not DC. And so all of these are sine waves, right? With no DC offset. The only thing that's DC is 0 hertz is this. All right. And like, oops. And like Jeffrey had mentioned, yeah, I would try to use a low pass. And you see how I'm drawing it where it goes straight up and down? The name for that is brick wall, right? Meaning you just want that and you want nothing else. The thing is there's no such thing as a brick wall filter that you can actually make, but you can keep trying to make it sharper and sharper and sharper, right? Now, yeah. Let's talk about as low as possible. So that's omega naught, or let's just call that omega 1, omega 2, omega 3. These aren't harmonics anymore. These are the cutoff frequencies from the Bode plot, right? And so now let's so omega 1 is the smallest, right? And so right, its 5 tau is going to be that. Then omega 2 is in the middle. And so its 5 tau is here. And then omega 3 is going to be like that. Its 5 tau is the smallest. So the thing is when I turn this, so here's the thing. We say that this waveform has been going on forever, but it's not really, right? We turn the thing on and then it starts oscillating, right? And so what's going to happen is that the one with the longest, the largest cutoff frequency is going to have the fastest rise time to where it's getting, right? The one with the lowest cutoff frequency is going to take the longest before it's available, right? And there's something that we're making it look like it's just going to be a flat thing. But what really is going on right, is that you can never get it like that. It'll kind of, just use some yellow here. It'll kind of do this, and you're going to be grabbing some of the things you don't want, right? And so the faster you make it, the more of these are going to leak in. And that's later, right? But the way I had asked it, make a DC power supply. And I didn't say how fast it had to be ready. So the answer, make a DC power supply with a cutoff frequency as low as possible, was a really good answer. It was an as low as possible really was an extra thing that made it a better answer. Okay.
Does that mean that the bandpass was the closest?
No, the bandpass, listen, I'm trying to be nice here, but the bandpass is as wrong an answer as it can be almost. That's why I wanted to know what everybody was thinking about, because Bandpass just gives you a particular frequency.
Oh,
Okay. It's, you know what I mean? We're all learning here, and I'm not trying to, I find that it's easy for me to embarrass people unintentionally, right? So I try to be careful, but each one of these, right, is a sine wave, right? So, here, let's just download it. Maybe that'll allow.
So to get this straight, the goal was to get the signal to be a flat line.
Right, DC, right.
Oh, okay, so yeah, if that's the case,
Is
then
that where I
at
went
least
wrong? Yeah.
no. Before you, I think what you asked previously was which signal best represents that square wave or something like that, and that's part of the reason why I chose band because it kind of looked like a band. But I didn't hear you say that you wanted a flattened signal from that. If that's
Okay.
the case, then I would choose a low pass.
Yeah, I had mentioned, I know I had said those words. I didn't realize I'd said it in that context, but thank you for telling me. I appreciate it. Yeah, that whole thing. Because it was here, I said, I want to filter, here's this, and I wanted DC. This is where I drew it. I'm not trying to.
Okay, I just
Not trying
misinterpreted
to,
what
but
you asked. That's all.
okay. All right. Yeah, so I think, so anyway, here's the file, right? So here's A naught. So if I were able to make that perfect filter, that'd be A naught, right? But then, let's say I wanted to do B1, that band pass, right? That would be B1, right? If I'm just clicking. Oops. So if I had a perfect band pass, I would get this blue line for if I centered it at B1. If I centered a band pass at B5, I would get this green line. If I centered it at 7, I would get this red one, 9, aquamarine, and 13, this nice purple. I'm going on at a limb here, maybe a fuchsia, I don't know. But now we can even see that even better, right? And then if you look at this sum, I'm summing these all back up, right? That would be the original square wave, right? If I took an infinite number of these and I had infinite precision in my calculations, right? And even if you were to do this with, well, that's a digitized circuit. I'll use op amps in continuous valued system. There'll be noise in the continuous value system that will prevent that from happening as well. All right. So now to ask the next question, I think I'm going to have to redraw that a bit.
So it is impossible to turn a DC, turn a square wave into a DC power supply then?
No, you can. It's just there'll always be a little bit of ripple. So you can turn it into a DC power supply within specification. Right? These are mathematical constructs which only exist in mathematical land, right? As engineers, we exist in the real world, even when using complex numbers. Yes, that's dad humor at its finest. But so like a mathematical DC signal, right, is something that's been constant forever in the past and forever in the future. It's never changing. A phasor, right, which is a sine wave with an amplitude and a frequency, has that amplitude and that frequency for all time, right? That's how the Fourier expansion works. But we, you know, you will have a Scopy device, you will turn it on, you will turn it off. If you use function generators before, you turn them on and you turn them off. And what happens is, if you leave them on long enough, it appears that it's been on for a long time. And if your system has a certain tau, right, and that system could include your oscilloscope, your probes, and some kind of RC circuit, right? If that system has a 5 tau of 1 second, you know, after 1 second, it'll appear to be repeating, right? And you won't, it'll look for all intents and purposes that it never changes, except you must have seen that whenever you measure anything, things are bouncing up and down slightly due to noise. And sometimes they bounce up and down wildly due to noise as you walk near it, open the door, turn the lights on. You know, circuits, you know, just because we have R, L, and C passive components in a compact model, meaning there's no dimension to it, right? All of these devices come from Maxwell's equations, and Maxwell's equations are always on, if you will. They're always valid. They're always there. And so everything can act like an antenna, receiving or transmitting, right? So anyway, maybe a little more philosophy than we wanted for today. So the next question is, I'm just going to say, I want to go from, I have a 0 to 1, you know, 50% duty cycle, right? And I want to make a square wave with no DC offset, right? Don't worry about the amplitude. You just want a square wave because because if it's too small, right, you're going to use an op-amp circuit to amplify it. If it's too big, you're going to use an op-amp circuit to make it smaller, right? So really, all we want is some kind of filter, right? Our choices. Right? What kind of filter will take this and turn it into this, right, with a no DC offset? Anyone? Okay, so I see one high pass. Anybody else want to go along with that for the ride?
But yeah,
Okay, we got 2, 3, 4. Okay, so let's just draw it the way right. So now, yeah, the way I drew it, it looks like I'm cutting this off, right? But really, that's just a constant amplitude. All that means is all of these get scaled by the same amount, right? And so it's blocking, right? And so sometimes you're going to have these signals, right, that have some DC plus sign, and you only want the sign, and they'll call this a blocking cap. Okay. And what they're not showing you is that this resistor, right, it exists. It's just so big that it looks infinite. Although some will put a resistor there so that you're not getting a random omega naught there. Okay. So what kind of filter would I use if I want A0, I want A1, I want A3, not A5, A1, A2, that's A3, 7, 9, and everything else. The one I don't want is A5, which would be this guy. I just want to get rid of a particular frequency.
Would we use the notch for that one?
Yep.
Yeah, the notch.
Yeah. Which I would draw like this. Right. And if I wanted to get rid of 2 frequencies, I would just kind of draw it bigger. Okay.
so what's with the notch filter?
Excuse me?
I heard someone say notch filter.
Yeah, notch filter. Great. Good answer.
For what now?
Hey, Justin, it's a notch filter. What I said is that you can get rid of 1 frequency, or a notch filter can get rid of more than 1 frequency, right? So you can just draw it
Oh, I see.
to whatever you want, right? Like a band, right? This is like a band for 1, but if I wanted 3 of these frequencies, right? And so so the thing is let's see if this will. Okay, so I'm thinking this is Italian, right? But I see Hertz, a spectre, which looks like spectrum, nota, notes, right? Of a piano, right? and this is intensity, right? It happens to be in decibels, right? And so you have the fundamental, there's a fundamental frequency, and then you have C2, 3, 4, and so on. So when you play one note, you're going to get these harmonics based on the first note. And so what I could do is say, well, I want to make a music synthesizer, right? And so I'm sorry, I have to look it up, but so middle C on a piano is 262 hertz, right? So I can have a fundamental frequency of 260 hertz, and then I have these other frequencies that come along with it that make it sound like a piano. And you can see that has a certain intensity, and then I have larger intensities, and then it kind of comes and goes, right? So what I can do is take a square wave and then select the ones I want and then amplify them and maybe attenuate them to where I can get something that sounds like a piano, right? And that would be additive signal synthesis, right? Sometimes you can have subtractive, right? Or, yeah, all right. So that's just one application, right? Although for music synthesis, this is just an aside, right? That the 50% duty cycle square wave, right, gave us an A naught and then BNs of 2 and pi n's are odd, right? So in fact, the triangle wave gives you all the harmonics you want. I mean, not infinite, it's just you get the evens and the odds. Okay. So that's why actually a triangular wave is used more frequently for that kind of thing. And even still, that's more like an analog synthesizer, not a digital synthesizer. All right. So I want to so this is another way that it can be used, this analysis can be used. All right. So what we have here, right, it looks just like an RLC circuit, except this is a square wave, and what we're trying to do is send a signal from the outside of the chip, right, through the wire into a pad of a chip. All right. So these wires here are the external part of the chip. Then when you open it up, you see these little pads here, and there's wires that come down to it. And then it connects to the actual piece of silicon, right? So these wires, right? Wires we're always saying is 0 ohms and 0 everything. In fact, have resistance, inductance, and capacitance. Actually, the triangle wave isn't that bad. But the thing is it's already, a lot of times you just look it up, right? Or you use SimP, or I might ask you to do a triangle wave or a square wave, so you're learning the process. But as an engineer, I don't go and resolve it, right? You just have the equations, just like you use an integration table, right? So I'm trying to find this. All right, but so here's the thing, this makes a filter, right? So this is the outside, these are the wire, represents the wire to get to the pad on the inside. And so we find the transfer function, right? I have ZR1 and then ZC is in parallel with ZL, right? Which there's a transfer function right there. And that's a notch filter, right? Because notice, if I just had S squared divided by the denominator, it'd be high pass. And if I had just had 1 over LC divided by that denominator, it would be low pass. And for a second order system, if I add the high and the low, I get a notch, right? And so, what's considered, how many harmonics do you have to worry about, right? A lot of times people say 7th, right? And so if I look at, this particular example, right, which doesn't, these are estimates, it's not a real chip. I didn't have one to measure, but you can see that there's a, right around, there's the notch is happening, and that's 10, around 20 gigahertz is right where that notch is happening for this example. All right, so let's just, so here I have a 50 megahertz, right? So that means the first harmonic is 50. Then the third harmonic in a square wave like that would be 3 times 50 megahertz, and the 7th would be 7 times 50, right? So this is another, and so what this is the input is a 50 megahertz square wave, input is 70 megahertz square wave, and it's kind of looking like a square wave, right? Even at 130, 160, but notice at 10 gigahertz, this is the output of the pad, right? That's what's getting sent in. And it's not looking like a square wave any longer. And then at 20 gigahertz, right at the notch frequency, right, it looks like garbage. And then when you go higher, it's just ridiculous. Okay. So in general, that's why to get a signal off and on a chip, you're kind of limited to 130 megahertz. This example kind of shows that, you can go faster, right? But that's because the example parameters are such that it's not happening at that. Also, the faster you go, there's like a power consumption, and the chip would heat up, and you couldn't use it. So really, kind of almost the fundamental limit of how much you can do on a chip is actually how much heat it can dissipate. All right. So what we have here is we have an input sine wave. And I have this sine wave squared. All right. So a quick way to look at the frequency spectrum is to do the fast Fourier transform, which you can do in LT Spice. But notice the period of the original waveform is 1 millisecond, right? But by taking the square, right, this now becomes positive, and I've doubled the frequency. All right. But let's look at the FFT. Now, this is in dB, of course, but really a lot of this, in fact, is noise from the calculation, which now you can see just, I have the first harmonic, and then where I square it, I have the second harmonic, right? But notice there's no DC here, right? But clearly, right, if I, let's see, right, here's 0. It never goes negative, the blue line, so that there must be a DC offset there, right? But on the green line, you can see that the time it spends on is equal to the time it's spent off. The Fourier transform strips out the DC information as part of the algorithm. All right. So sometimes it's just easier for me to create it than to find. I do have a tremendous amount of examples. Almost as if I need my own librarian. Right? This should give me a gain of 2, right? Looks pretty good, right? now V test, right, is really just V test 2 is just V test times 2, right? And you can see that the harmonics are, lining up, and that there's just a, one is just bigger than the other, right? But what if I had a gain of 10? All right. That doesn't look like it's squared anymore, right? And this will pop out. And notice, before we had the test wave that had its frequency. Then the squared wave had a fundamental frequency. But now the one with the gain of 10, yeah, that frequency is still there, but all these extra harmonics are there as well, because it's no longer a pure cosine squared wave or sine squared. You can use to test multipliers, right? Because the other way would be is to just do a DC sweep, right? And so V in is the input, right? V test is where it's just squared. And notice you get a parabola, right? However, when you put that into a real op amp with supply power supply limitations, yeah, it's a parabola, but this is cutting out here. And so rather than trying to curve fit this, right, people just run it, and then they look at the fast Fourier transform, which we already did, right? And when you see, and there will be always harmonics that you don't want. The question will be, are they small enough to be used for your application? All right. Okay. So now, as far as the homework is concerned, question 1, we did that last time too, right? You just have to do that mathematically, right? We have some questions, right? What parts of the spectrum would you keep if you wanted this? What would you do if you wanted DC, right? So we've answered that. And then, yeah, here's a cubic, right? You probably want to use a lookup chart or, SIMP, right? So we have 50% duty cycles. I want to convert this to a DC. I want to convert the signal to an amplitude that has 500 kilohertz. What if I wanted a 100 kilohertz signal, right? So we've kind of done that. Here, right? What I've done is I've multiplied things by sines and cosines, right? So this is V pulse, right? So how would you numerically estimate A naught, right? Well, find the average area, right? Now here are the cosines of F1, F2, F3, right? How would I estimate it? Well, I draw a line through it and it looks like the positive and the negative cancel each other out. So it's zero, for the A1 would be something like 0. Here, right, I'd have to sit down, but they might cancel out. Here, 1 up, 2 down, 2 up, 1 down. That looks like it cancels. And then for the sine waves, right? Oh, that's always positive. And what I mean by estimate is you can use a triangle and just get, is the area positive? Here, I can use triangles, but it kind of looks like it cancels out. Here, it looks like I have, you know, a lump up, a lump down, and a lump up for a total of 1 positive lump, and use a triangle to find that area, then average it out over the whole thing. Okay. So that's how you could find that. And yep, Rayad, yes, I wanted you to do the triangle wave too. Okay. And just plot out the first 7 terms. And then the last one, it's kind of like just logic, right? So I have a 1 kilohertz pulse wave with 25% duty cycle. All right. So I start looking for things with 1 kilohertz, right? Oh, they all got a kilohertz. Okay. It's got a 25% duty cycle. All right. And since 0 is 0, the low is 0 and the high is 1, that's got to be an average of a quarter. All right. Which one of these A naughts gives me a quarter, right? Here's something, it's a pure sine wave with a DC offset. So I'm looking for something that has a DC offset and a sine wave, right? Here's something that has, it's all sine wave and no DC offset. And then you have a 50% duty cycle, right? So you can almost do them by eye. All right. But the 50% duty cycle one, we've already done. You know that it's going to be odd harmonics. All right. So you don't actually have to find the full blown spectrum of each one of these, right? You can just puzzle it out. But that's pretty much the homework. Next time, we're going to take a moving platform and a damper system with a spring and a mass, and turn that into a voltage, resistor, inductor, and a capacitor. So the thing is you can model mass spring damper systems in LT Spice. You can do a Bode plot of a mass spring damper system, right? You can find the damping coefficient, right, of a mass spring damper system. So everything you learned in circuit analysis, you can use once you convert this to a circuit. And yeah, what happens if something breaks completely apart? What if it freezes? What if somebody's lying about the mass, right? So that's what we're going to go over next time. All right. But today's the Fourier, for the midterm, again, there's 5 questions. I don't know why, but I always put I've been putting the Fourier in question 5 and mass spring damper like at 3, gain bandwidth at 2, the DF2 question at 1, and then this is controls. All right. But for whatever reason, I have it like that rather than in the order of presentation. But that's really what the midterm will be about. Okay. And for the Fourier questions I've used in the past, I've used questions like 7, and then 5, but also these, what kind of filter would you do if this were the case? If you wanted this, what kind of filter would you do if I wanted that, right? That's pretty much it. Any questions before you all head off? And I'm pretty sure that they changed the 112 midterm date already, but that should be done.
Actually, I got one quick question.
Sure.
Oh yeah, for question number 5, I didn't completely understand what the question was asking. Yeah, for number 5, what exactly are they asking us to do?
Using the plots from the waveforms shown to estimate the Fourier coefficients of A0, AN, and BN for the square wave shown. So rather, if I just said, find me A0, A0, and B0 for a 50% duty cycle square wave, well, we've actually already done that mathematically in the notes, right? I want you to estimate it. And remember, right, how do you find A0? You find the average of the signal. How do you find A1? You find twice the average of the signal times a cosine wave at the fundamental frequency. How do you do it for the find A2? You find the twice the average, right, of the signal times a cosine with twice the fundamental frequency. What about 3? 3 times the fundamental frequency, right? So what I've done is I've made sine waves and multiplied them by these things so that in fact you would, yeah, an LT splice, you could click on it and click average, and it would actually give you the coefficient. But I'm wanting you to do it by estimating it. And that's where, like when I'm saying use a triangle.
Oh, as in do it. You mean
Yeah,
like do it
no,
through its-
actually, hold on, I can't. I clicked the wrong thing here.
You mean do it through inspection rather than through math?
Well, if you can see that it evens out, I'm sorry. That's gone into an infinite loop. So if I can tell that something evens out by looking at it, then it's effectively, and if you can't tell that I mean, it's like, if that looks like it's zero, then compared to everything else, it would be zero, right? But notice I have half a cycle up, two kind of shapes down, two shapes up, half a cycle down. All right, that's looking like it cancels out. And darn it. Listen, I think we're out of time.
It's okay.
If you look at other case studies and exam samples solutions, you'll see that I'll just put in a triangle, find the area, and then divide it by the period to get the average area, right? So that I come up with a rust estimate, right? So things are going to be like very close to 0 or 0, and then either a positive number or a negative number. The ones we did today, everything was positive, but sometimes they're negative as well. Okay.
Okay.
And again, you can see me in office hours or anything like that. All right.
Bye.
All right. Take care. Oh, this is not.